This is the first of 3 lecture segments dealing with climate change, the science of climate change and its communication and use and environmental management policy. This first segment will address climate change basics. From there, we'll go on to another segment dealing with various climate change assessments that have been undertaken from global to national to regional scale. And then finally, we'll consider science, climate change science and public communication and understanding. This particular segment helps us understand the greenhouse gas effect, become aware of the milestones in climate change science, explore the evidence of changing climate and its attribution, and consider the multiple consequences of a warmer and more CO2-rich planet. And then finally, we'll introduce just briefly the need to limit climate change and adapt to the changes that take place. So the next 3 slides show you sort of the extended history of our understanding of the greenhouse gas effect and how it affects the climate. This understanding developed actually early in the 19th century with Fournier, basically understanding and describing how there was this heat trapping effect of the Earth's atmosphere and how that it kept the infrared energy that was radiated down to the Earth by the sun, from all of it from leaving and therefore warming the atmosphere, keeping the planet warmer than it would be otherwise. So Tyndall, in the mid-19th century, described this heat blocking effect as a feature of the carbon dioxide that was present in trace quantities in the atmosphere. Later in the century, Arrhenius calculated that this warming effect would actually increase as the CO2 increased, and by then we knew we were adding CO2 into the atmosphere from burning fossil fuels. So he estimated the effect of warming of the planet if we double the concentration of CO2 in the atmosphere. There were controversies at the turn of the century related to whether this was actually going to happen or whether there were some other effects, interaction with CO2 and water vapor. And Arrhenius then refuted these criticisms and showed that water vapor, H2O, has little impact on the upper layers of the atmosphere. So the progress continued in this understanding, in which various scientists had estimated the effect of warming, estimating that there would be about a 4 degrees C from a doubling of the CO2 increase. That increase affects not only the CO2 concentration, but as the planet warms, the water vapor, the H2O in the atmosphere increases, and that would have a feedback effect. That was well understood earlier, the first half of the 20th century. And then we began making more discrete and specific proposals and projections about what the increasing concentration of CO2 in the atmosphere would portend. A couple of the individuals I've indicated here on the pictures to the right. One notable individual is one of the really fathers of oceanography, modern oceanography, Roger Revelle, who was the director of the Scripps Institution of Oceanography for many years, and a geochemist, who understood and described the uptake of CO2 from the atmosphere into the ocean and how that would change the ocean acidity over time. In addition to that, one of his associates, who Revelle sponsored, was a gentleman by the name of Charles Keeling. And it was Keeling who developed some methods to be able to measure directly the CO2 concentration of the atmosphere and deployed them on an observatory, long-term observatory on the top of Mauna Loa in the Big Island of Hawaii, ostensibly removed from local sources of CO2 input. And it's this Keeling curve of CO2 that is really a compelling bit of evidence in terms of the enriching of the carbon dioxide concentration of the atmosphere. Moving on into the latter part of the 20th century, There were more specific modelers. Manabe, who was at Princeton, NOAA's Geophysics Fluid Dynamics Lab at Princeton, Tom Wigley at the National Center for Climate and Atmospheric Research, and James Hansen in NASA. Interestingly, all three of these individuals were essentially worked in government agencies or government-sponsored laboratories, and they helped us understand the changes that were going on and likely to go on as this increase in greenhouse gases from human activities progressed. So we have this increase in CO2 concentration that we see here from the Keeling curve. And when Keeling began measuring it, really by 1959, we see this very continuous trend with an up and down seasonal signal as the northern hemisphere plants take up CO2 in photosynthesis in the summer and release it later in the year when respiration dominates. We have now topped and probably won't go down below for a very long time, if ever, the 400 parts per million level that we were all concerned about. Just this week, last week, it was about 407 ppm. But even more importantly, this level is really unprecedented. Recent work on looking at CO2 captured in ice cores, bubbles in ice cores from Antarctica, actually extended this period in which we've not seen this level of CO2 to about 4 million years. So we're here at this period where there have been these increases and decreases in CO2 that run along with the changes in global temperature. But they more or less coincidentally, and I'll talk about that in just a moment, but we're now here up over 400 ppm at concentrations that haven't been seen in at least 4 million years on Earth. And the reason why there is this coincidental behavior of CO2 concentration and temperature is obviously the greenhouse effect. And so these records were criticized by skeptics by saying, well, temperature increases before CO2, so therefore it's not CO2 increases that causes the world to warm, it's temperature that causes the CO2 to enter into the atmosphere, which is essentially true, but in which the cycles, the Milankovitch cycles of the Earth's rotation and wobble initiate these periods of ice ages as the temperature declines and increases. And when the temperature begins to increase, the oceans warm, tremendous amount of CO2, which is stored in the oceans, is released. And so that's been a natural greenhouse gas effect that's caused this warming trend. But now we're kind of out of sorts because this increase in CO2 is not due to this natural cycle of CO2 exiting the ocean, but actually humans taking fossil CO2, fossil carbon, burning it, and putting it into the atmosphere. So the thing to keep in mind also is that CO2 is not the only greenhouse gas. There are a number of others. Obviously, the atmosphere is mainly made up of nitrogen and oxygen, which is not molecular structure is such that it doesn't become excited with when it receives long-range infrared radiation, and so that doesn't have the warming effect. But it is these other gases, notably carbon dioxide, methane, and nitrous oxide, which actually can have the CO2, have this greenhouse gas effect of insulating the Earth, keeping infrared radiation into the atmosphere from radiating back to outer space, and therefore causing this warming effect. So interesting, you see all of these three greenhouse gases have all been increased in about the same time period since the Industrial Revolution, more or less, and for reasons related to human activities in all cases. the record is pretty clear for CO2, as we reviewed. So we've had about, since the Industrial Revolution, about an increase of about 44% of the CO2 concentrations in the atmosphere. And for methane, about 150% increase, and for nitrous oxide, about a 21% increase. Interestingly, though, importantly, though, that these greenhouse gases don't last the same amount of time in the atmosphere. CO2 lasts a long time, an average of about 200 years once it's in the atmosphere, whereas methane is has a short life. It's oxidized to CO2, actually, in the atmosphere, and nitrous oxide is somewhat intermediate. These other two greenhouse gas elements, they are much more potent greenhouse gases, molecule by molecule, than CO2, methane by 25%, and nitrous oxide by 296%. But they are lower in concentration. So we estimate the total combined effect, often expressed in concentration and CO2 equivalents, based upon the degree of the degree of effect of a molecule of one of these greenhouse gases and its longevity into the atmosphere. So this is a recent record since 1970s, late 1970s, of the temperature data. These are multiple, 5 different sources of estimation of global mean temperature. And you can see it's a noisy planet. It's a noisy world with high variation over years and decades in temperature, global mean temperature. There was much made of the fact that since 1998, which had a strong El Nino, was a strong El Nino year, very warm, record warm year, that there's been no increase in temperature. Even some would suggest that global cooling, or this phenomenon, has been called a pause, and caused a lot of mystery among scientists about why that was happening, and also among skeptics of saying, well, so much for global warming. It's not continuing the way you thought it would be. However, if we looked at the natural processes which affect these, the temperature, including the El Nino effect that I mentioned, which heat is coming out of the ocean back into the atmosphere, as well as solar activity and aerosols that are released by human activities, which shade the planet, causing a cooling effect. If we factor all of those in, we get an adjusted record looking like this, pretty much a more continuous trend of upward warming. This is data through about 2011. So again, here we have the raw data, but once you adjust it, this slowdown effect tends to dissipate, and this is more clearly a signal of human activities in this filtered record. Putting it together in another way, this is very recent. This is just actually has the data in it through February, showing the temperature trend, same multiple data sets. In this case, further adjustments were provided on these data because of some new discoveries about aliases in measuring sea surface temperature, depending upon whether you were in the old days using buckets or underway vessels sampling with cooling with water coming in through the cooling systems of ship, or from buoys that were deployed. Once those were ironed out, this cooling trend, or the hiatus, became less obvious, particularly if we factor in these recent years, warmer years, 2014, 2015, 2016, in which the instrumental record warm temperatures were broken in each year. If we put this in the context of what the models tell us about how the climate should be behaving, you can see there's a very close relationship. And even during this period of a little bit slower warming, you would find that it's within the natural band of what we would call to expect because of weather variations, and well within the the bands of the model estimates. In fact, it's pretty well on track on these long-term trends based upon the greenhouse gas concentrations as well as these other forcing factors. So if we then try to factor out what are the forces that are causing warming or cooling in the planet, we'll see that if we compare the observed warming to that warming that we would expect by just due to the greenhouse gases, we actually find less warming than would think based upon the greenhouse gas concentration increases. But that's because there are other anthropogenic factors, particularly this aerosol effect, which is causing some cooling of the planet because of the shading reflection of solar radiation coming in. If we combine those, we actually get a forecast, a prediction, an explanation, an attribution of the warming effect, which is pretty much matches, certainly within the error bars of the observed pattern. And natural forces are actually very small in this, mainly thinking of things like volcanoes, but also solar activity. And that, in fact, if we then estimated it on a probability basis about what would be the effect of these attribution of surface temperature trends based upon the anthropogenic human forcing, we basically, the best estimate is about 110%. So we're stated another way, virtually all of the warming we've seen is due to human activities. There are other forensics, there are other indicators of that, both of this warming trend as well as the human source of it, summarized in these slides. And they include things like sea level rising as a result of the warming ocean, the melting of land-based ice, increase in humidity, decrease in snow cover, the phenology of plants when plants are leafing out, blooming, the migration of species, the ocean heat content, we'll show you that in a little bit. So all of these are multiple fingerprints of the fact that we've got a warming world, regardless of the debates about the temperature record and the adjustments there too. Why do we know that this is caused by human activity? Well, we can see that there's less oxygen in the air, so if there's more CO2 from the combustion, the oxidation of the carbon, it's brought down the oxygen levels, so that's an indicator of this is from combustion. We've got more fossil fuel carbon in the atmosphere, measured by stable isotope ratios. Similar thing in terms of what we observe in terms of the carbonates laid down in coral skeletons. We have importantly, less heat escaping to space, so that at the base of the top of the troposphere, the base of the stratosphere, we actually see cooling because of the greater insulating capability of the blanket of the atmosphere over the Earth. As a consequence, then, most of the heat that the planet is accumulating is not in the atmosphere. Actually, it's in the ocean. You can see here only a small part of the heat built up is a result of the increase in heat content in the atmosphere, and also the decrease in ice as a result of the heating of that ice. And most of the heat buildup is being stored in the ocean. And this is a very recent study which has basically shown this in greater detail and indicating that there's a significant more 15% or so more heat than even this estimate indicated being built up in the ocean when we actually take the best measurements we have in place. And this is very consistent with what the anomaly of the TOA, the top of the atmosphere, in terms of the return radiation, but at the top of the atmosphere back to Earth. So again, we see this effect. Here we see short-term effects of volcano eruptions which actually can reverse the the heat accumulation for a short period of time. And we can see also the heat is reaching to deeper and deeper depths. Here, the heat content of the various depth layers of the ocean are indicated. So this is pretty clear evidence, again, that we have not only the total warming of the planet, but also there's a lot of heat built up, inertia built up in the system that's going to keep the planet warm. Finally, I should say that there's a big criticism often, because you might have heard critics say, who disbelievers of climate change, say, well, you used to call it global warming, now you're not so sure, so you call it climate change. Well, it's actually both. It is global warming, but there are more things happening than just the warming of the planet. There are other dimensions of the climate which is also changing. And notably, this includes precipitation patterns. These actually are projections rather than actual data. But they show basically this trend of increasing precipitation around the equator and decreasing precipitation at mid-latitudes, particularly these already arid areas like in the Mexico and the U.S. Southwest, the North African deserts and the like. You can also see these trends here in the United States. These are actual observations, trends rather than model results, showing that in most parts of the United States, there's been an increase in precipitation during the 20th century, from the first half of the 20th century to the last last 3 decades of the late 20th and early 21st century. And that's not distributed uniformly, with drier conditions developing in the Southwest and to a certain degree in the Southeast, consistent with this mid-latitude trend that I talked about earlier, and greater precipitation trends in the Northeast. In addition to this, again, consistent with the concept of a warming world, more of the rainfall is coming down in large events, large heavy rainfall events. So the climate is changing in many ways. The intensity, the amount, and the frequency of changes, both precipitation as well as drought conditions. So you have more of these problems with fire and so on in the Southwest, because you have longer drought periods and generally drier conditions, and floods and unprecedented flooding events and so on in the Northeast and some other areas. So as scientists, this is from the Intergovernmental Panel on Climate Change, have tried to assess what are the risks of this warming. This figure is often used, often referred to as the burning embers diagram, which shows you, if you take various issues that you'd want to be concerned about, unique and threatened systems, extreme weather events, and these large-scale global events that are global or subglobal events that can be of great consequence, and the temperature indication of these indicates how intense and how substantial these changes would be based upon an increase in global temperature. So on this basis, it was concluded by the IPCC and as a general scientific consensus that if we got to the point where we were warming the planet more than 2 degrees average temperature over a sustained basis, we would have very significant changes, irreversible changes with great consequence. So this is the basis of the Paris Agreement that you've heard about, done in late 2015, to take action to try to limit the increase in global mean temperature to no greater than 2 degrees C. At the end of that agreement, though, there was a thought that, that's actually pretty risky as it is. And so there was another effort to try to be more ambitious and look at, can we actually keep the temperature from warming more than 1.5 degrees? And we'll be talking about that a little bit later on. So the challenge before society is to take action that would limit the amount of warming, whether we can hit no more than 2 degrees C or more than 1.5 degrees C. We'll wait and see, but these efforts are generally called mitigation. Generally, they require reducing emissions, limiting the increase in concentrations of greenhouse gases in the atmosphere. There are other things that could be done as well. But then, despite that, the fact of the matter is the climate is already changing and will be changing even if we can achieve these results because of the inertia in the climate system. It changes even more, so that we will have to make adjustments to manage the effects of climate change. So this is what we call adaptation. So these two terms, mitigation and adaptation, are terms of art in the climate science and assessment business. So finally, let me mention one other manifestation. It's not really climate change per se, but of the buildup of the increase in CO2 concentration. And this is the phenomenon which is called ocean acidification. For the most part, the oceans aren't acidic, but it basically is reducing the pH of the world's oceans because because more CO2 is being dissolved into the surface waters of the ocean. And of course, then mixing down, the CO2 reacts with water to produce carbonate ions, essentially carbonic acid, which basically lowers the pH, but also makes it difficult for organisms which must form calcium carbonate for their shells, skeletons, and the like. And so this is the great concern about the acidification of ocean waters. And here you see this picture of the past over millions of years of what we knew about the fluctuations of the world's oceans and where we are now, down lower than we have seen in some million years, several million years. But with that, if this trend continues, we will see low pH that we haven't seen in a very, very long time in Earth history.